Now coming to some routing schemes. Static, dynamic, hop by hop, flat, hierarchical. We're still not there, fully there at the internet routing protocols, basic schemes. Okay, routing scheme, we learned, okay, this is, well, to exchange topology, parts of the topology, information about the topology between the routers, so that then the routers locally can make the correct forwarding decision. So what is needed for routing schemes? Most important thing, scalability, because we have a huge worldwide network. So the routing scheme should be able to handle this worldwide network somehow, and it should somehow also converge to a result. You can imagine there are many routers coming up, going away, and somehow this, well, you have to calculate optimum paths. But the network is not static, it's dynamic. So then also the overhead should be quite small. So we cannot load our network with a lot of routing traffic. Just imagine, I mean, all the routers only have to think about routing and the network handles half of the traffic is routing traffic. That doesn't make any sense. So only a bit of the traffic, only a small percentage of the worldwide internet traffic should be routing traffic. The router should be able to handle the routing itself with a normal standard CPU, memory, software. And you don't have to use specialized hardware for this. Then it should be extremely fault tolerance, so maximum availability. The network shouldn't go down. No loops and all these things, and maybe also different paths for different applications and all these things. As I already mentioned, routing tables can be large. So it's quite important to ask how to structure the content. We all know by now we do not store IP addresses of end systems in a routing table. We store network prefixes, but still, this can be quite a lot. So many prefixes. How do we structure this in the routing tables? Then, how to maintain them? Are they always 100% up to date? How do they really reflect the current status of the worldwide network or of parts of the network? Can they do this? Can we tolerate some inconsistencies? So how do we maintain this? Do we update every second, every minute, every whatever? So there are different possible ways of structuring the routing table, creating routing table, maintaining routing table. And the following slides just give you examples of how you can do this. There are some simple ways. Maybe you can do this in smaller networks called static routing. So basically, in static routing, it's very simple. There's no complex routing. So you create following certain rules, your forwarding table, and you use them in the routers. So very simple. You configure manually whatever if there is a certain destination. So in the router number 4, if someone wants to send packets to to node 2, whatever, then go via interface L2. So very simple. As simple as this is, there are, well, some advantages, yes, but also big drawbacks. What happens if a link breaks down? If a router breaks down? Well, you cannot react. You have fixed programmed tables. So this is why we don't use static routing. We always use dynamic routing. So we have to track the network continuously. Yes, this is some overhead, but that's the only way to be fault tolerant. Have a higher reliability. Yes, it's more complex. You have more overhead, but how else should you react on failures of links? So typically we favor dynamic routing, and static, you cannot use this in larger networks. Maybe for small networks, maybe for fixed configurations, you could do this. But in real larger networks, you have to go for dynamic routing. What else? Well, there's something called source routing and hop-by-hop routing. The idea of source routing is that the path is fully, or at least partially, determined by the source. And the source then includes the path in the packet. So for example, if you want to send something from node 1 here, that's our source, to node 7, that's our destination, you could say, okay, I know it. How? That's a different question. But I know that for doing so, I have to send from 1 to 2, and then to 3, and then to 4, and then to 6, and then to 7. So that's one of the ideas. And by the way, in the original implementation standards of IP, that was one possibility, this source routing, not used. That there are also routing protocols in the mobile domain that can use source routing, but there are some problems with this. Yes, it's nice. The routers can be very simple. They don't have to know anything because they get the direct order. So router 4 here, for example, reads directly here in the list, okay, the next one is 6. So there are no alternatives. Very simple forwarding here. But what about fault tolerance? What happens if the downstream router breaks or link doesn't exist? Then what should you do? If this link doesn't exist anymore, then what to do in router number 4? You cannot then reroute via 5 to 7. Doesn't work. And sure, the question is, how do we know this path? How does the source not know this? There are certain ways for so-called path discovery, more in mobile communication. So that's one way of doing it. We don't do this in the internet. We do in the internet hop-by-hop routing. So the path is determined by each intermediate router. So we cannot say, please take this path, but each router then checks where to go. So this is way better when it comes to reliability, fault tolerance. So if something breaks, we can reroute. But yes, we have to store state. And still, we are dynamic and we do hop-by-hop routing. So you see, there are different questions, and you can either do it this way or that way, and there are some good reasons for solution A or B. Here in the internet, we are dynamic and we do hop-by-hop routing. What else can we compare? Well, we can compare routing based on packets, or we can switch circuits. Packet routing, that's connectionless. So that's what we do typically in the internet. We check for this longest prefix match at each hop. There's the alternative solution, circuit switching. Well, circuit switching, that's connection oriented. So very simple, because you first set up a circuit, a virtual one, a real one. In former times, we really connected copper wires and with switchboards, etc. So you set up a connection, and then it's very simple how to forward. There's no longest prefix match, whatever. So it's predetermined the way to go. There are advantages and disadvantages for both. So the classical telco way, in former times, telephone network operators, they used circuit switching, connection-oriented circuit switching. That's also what the older mobile phone networks used. So they first had this setup phase, and then you labeled the connection with a short label. Short label, remember, we had this label switching, so you got a short label, maybe 17. And from this on, you set up the tables in the switches, and for forwardings, you simply match exactly. If a packet comes in, because there you also have very tiny small packets, but they now have the labels, for example 17, you know exactly where 17 goes. So routing happens only at the setup of this virtual connection. After that, well, it's static. So that's the idea. If something fails, well, the connections then also fail. Well, you can again set up a new path, so you can reroute everything, but this very specific circuit, well, it's dropped if a switch fails, but it's very easy to guarantee certain quality of service, because if you, during setup, ensure that the switches, the intermediate systems, typically they are called switches, that they can handle this virtual connection, that means they have enough resources to forward whatever, the 64 kilobit per second for a voice call, then you can guarantee the data rate. And also you have no problem with congestion, because you know after setting up the connection, you know all the parameters of this connection, and if you have the resources, nothing bad happens. On the other hand, if you do this connectionless packet routing, you don't need any setup. Okay, you just send in your packet. Each packet now contains the full source and destination address. For circuit switching, only at the connection setup. After that, you have this simple label. For forwarding, you do this longest prefix matching. Well, you can be more dynamic, so you can update routing info, and if you have a failure, you can reroute. You may lose some packets, but you can reroute. But what the real problem is, how to guarantee quality of service, how to do congestion control. In the internet world, we chose packet-based routing, although there are some circuit switching elements in the networks. These are details. And really, yes, it's difficult to have support quality of service. There are some approaches. You learned already something about differentiated services, diffserv, and the code points and all these things. There is some congestion control. It's a bit more difficult. We'll talk about early congestion notification. Why this connectionless? Well, big advantage, no prior setup of a connection. That makes it more flexible. Also, when something breaks down, the point is we don't know if all the operators of all networks always have all routers up and running, so that things can break. And for the packets, especially in former times, I mean, transmitting emails, if something goes wrong, you retransmit, etc. So that's a different philosophy compared to the telcos that always had these voice calls in mind. Today, it's everything over IP. So we don't have these circuits anymore. Everything is over IP. We have extreme fast networks, so we don't care about these issues with the for many times for this quality of service and so on. So in the internet domain, we went for packet routing, not circuit switching. Okay, and if we do this packet routing, then we decide in each router for each packet what to do. So if we have a packet that's forwarded from one process P1 to another process P2, all the routers A, B, C, D, E, and F, they decide how and where to forward this packet. So you see here an example. If you look at A, then you see, okay, initially maybe you have a certain setting here and telling you, okay, if the packet has a certain destination E, whatever, then we forward. So if A has to send something via E, it's just examples. So network prefixes, not the address of the end systems. So E is responsible, then we know this goes, for example, via C, and F also goes via C, etc. So, and that's the whole idea. So hop by hop, we decide where the packet should be forwarded. This can be changed depending on a certain situation. So maybe something breaks. So it could be the case that, for example, here, or that we have or something gets more expensive, then we may change this. That's up to the routing to say, okay, now we have a better path. Now we reprogram our forwarding table. That could be the case. And so this could be a setting for these different routers, the different tables. But each of the router has to have a table, and in the table, all the routers should know what to do if something goes to one out, in this example, 6 destinations. So there's a lot that has to be stored here. But we can react. For example, if something is cheaper, a line breaks, etc. So if we go for circuit switching, it looks a bit different. So in circuit switching, we set up flows, or virtual circuits, or connections, different names with slightly different meaning, but here that's not the important part. So here for per flow behavior, we also have certain tables, forwarding tables. But now we see that, okay, for example, if we set up a certain flow that says, okay, from during connection setup, the path is determined, and then A, here our A, only knows if something comes in from this H1 in RK, then it goes out via this C here. And the idea here is that we set, during this connection setup, we set the path, and in C it says when it comes from A, we go to E, but you also see that we assign certain labels to it. This is done during connection setup. So we do not only give determine certain paths, but we also say, okay, if traffic comes in from H1 with a certain label 1, we forward it to C and map label 1 also to label 1 in this example. Does this make sense? Well, yes, because now look at the second flow. The second flow coming from H3. Coming in also here labeled with label 1. Also sent towards C, but in this case we map the label to 2. Why? We can now differentiate those two traffic streams. One has a label 2 and one has a label 1. And maybe we can treat them differently. That's one of the things we can do. But what we can always do is we can perform a certain forwarding. We can also separate those two streams. And you see that here C, this node here, can still handle them separated. So we see it comes from A, it has the label 2, then I forward it to E, also with the label 2. So 2 is mapped to label 2, and 1 is mapped to label 1, although they go the same way, but it's a different virtual circuit, a different flow. Then in E, we see, okay, there's traffic coming in from C with the label 1. It goes to F with the label 1, and there's also one with 2, goes there with the label 2. So the idea is that we basically perform the forwarding based on labels. And during the initial setup of the virtual circuit, we program these tables. So it's not this hop by hop, and it's a distributed process, the routing, then we have the path, and then we fill the forwarding table. But it's this during setup where I say, okay, this is A's table, then B's table, C's table, and we have these two parameters stored, the source and a identifier of a flow or the virtual circuit for the incoming and for the outgoing. So which one is the next computer, switch, whatever, and the virtual circuit. So in this case, quite often those intermediate systems are not called routers, but switches. Why switches? Well, typically, when we talk about routers, we always think of this distributed process of routing, finding the paths, and then creating the forwarding tables using this, longest common prefix matching. If we talk about labels and switches, then we think of, okay, this is this, very simple thing of just taking what is the input port and the label, and we map this to our output port and the label. So, and this label switching was introduced also for many different protocols and under the term multi-protocol label switching, MPLS, and it had peak times, late 90s, 2000, and was one way of managing traffic. With the help of MPLS, you could, for example, do a very quick failover. If a route breaks, you could switch within milliseconds to an alternative path by simply having different entries in these tables, etc. So if you're interested in MPLS, please look it up. But MPLS really had its best times. Today, we see more and more these worldwide optical transport networks and everything run using Ethernet. There is still also MPLS and some other technologies. So label switching. Here we are still in the concepts. Packet switching, circuit switching. As I said, Internet, classical, what I then will present is packet switching. And this is just the pointer towards label switching. What else can we distinguish? Well, reactive routing, proactive routing. What does it mean? Reactive routing, that means, we try to find a path as soon as someone asks for it. So if we have a packet that has to be forwarded, then we find a path. That's cool. So big advantage, we don't set up paths for nothing. So as soon as there's data, we forward it. Way less overhead. Drawback is, this takes time. Because if we want to send something, then we find the path across the whole internet. This takes some time. So there's a delay for path exploration. The alternative is we do so-called proactive routing. So we try to find out all possible, or better say, all needed paths. We discover them before we need them and maintain them. Big advantage, there's no delay for path exploration. So as soon as we want to send something, there is a path because proactively we looked for a path. Big drawback is, we have an overhead. So no matter if we use paths or not, we have to maintain them. In the internet, we do proactive routing for the classical fixed internet. In the wireless domain, yes, we sometimes do this reactive routing because control traffic is not a good idea in the wireless domain. But here in our fixed networks, we maintain all the required paths all the time so that we basically have no exploration delay. Think of a worldwide network. This would take a long time before you find your path. Yes, this is an overhead, but talking about fixed networks, we don't care that much. So we go for proactive routing here. What else? Flat versus hierarchical routing. What does it mean? Flat means all routers belong to the same region. So we always know the full topology. So best paths are available. We know the whole topology. Great. Yes. The problem is, does this scale? You have to know a lot. The alternative is, we do some hierarchical routing. We define different regions. And within the region, someone organized this region, but we don't have to know the details if we are outside the region. So looking like a tree or a network or whatever, so we have a central region, try avoiding roots, etc., loops, but we don't have to look what's inside the regions. So we have less state. The routers only have to know their own region in detail, but maybe overall we don't get as optimized paths compared to the flat routing because we don't know the whole network. So maybe you have someone that overlooks all these domains, these cloudy things, but whatever's inside, you don't care. But if you're inside, you know everything, all the details inside, but you don't have to know all the details of all the other networks. And that's exactly the way we do it in the internet. So we have different systems that operate autonomously. So they don't let you look inside their system. They know how to handle their system. They know all the systems internally. And they know the rough topology of the outside world. They know all the other clouds, so to say. All the other autonomous systems, as they are called. But they don't know the precise topology inside other organizations' autonomous system. That's the only way really to handle this huge worldwide network. Flat routing, you can do this for small networks, some dozen nodes, but not for millions of nodes. Also some examples here. So assume a network as shown here. Then if you do flat routing, then basically the router 1A, this one, has to know everything. Has to know, for example, that there's a router 5D, and if there's a host connected to this, for 5D I go via 1C, and this is 6 hops. So 1, 2, 3, 4, 5, 6. Okay. Nice, but doesn't scale. So it's better to create certain regions and to perform hierarchical routing. Hierarchical routing, that means, well, I don't have to know the details of region 5. I only know if there's something going to region 5, then this goes via this 1C. So A knows if I go to region 5, then I go to 1C, and then whatever is there in there. So you see, with hierarchical routing, you can aggregate many systems, all those starting with 5 or all those starting with 4. Now you can imagine where we need our network prefixes. Those prefixes, they help us to aggregate all these systems. So we have much smaller forwarding tables. That's quite obvious. Okay, but now there could be the case that paths are longer than necessary. Why? Well, the point is, you don't always know the internal structure. And in this very simple scheme, it could be shorter to take this path than to take that path to go to a very specific node inside region 5. But as we aggregate, we have to decide which way to go. So, and then we decide for one of these paths to reach the region 5. And this might be not the shortest paths. So maybe the paths are longer. Yes, but because it scales better, we do hierarchical routing in the internet. We cannot do flat routing. That doesn't scale. So we have to aggregate. Yes, maybe we sacrifice sometimes the optimum here, but that's the only way to handle it. So now we saw different basic routing schemes: static, dynamic, source, hop, flat, hierarchical, etc. There are some more concepts. And one quite important concept is, well, how do we represent our network graphs? How do we assign certain weights to the edges of our graphs? Introduce certain metrics, because I quite often said, oh, this is an optimum path. Well, is shorter better than longer? Well, it depends. So there are some more basic concepts. And there's one very simple basic concept, and that's flooding. Well, flooding is a very simple thing. Why should we care about specific paths? Flooding. Flooding is very simple. Why? Well, packet comes in and we simply copy it. Oh, flooding. Very simple. Okay. Big advantage. Each packet reaches all other routers. Very robust. If there's a failure, who cares? Very simple. If there is a path, flooding will find the path. But you can imagine big drawbacks. I mean, yes, all the packets reach all the routers. So yeah, you can encrypt them. So privacy is not a problem. But potentially you have a dramatic output decrease. Think of flooding worldwide networks with your packets. And then we need loop detection. Okay, we have the TTL, so we have some storm at least until all the packets die. But flooding, well, sounds very stupid because of this extreme decrease in the output, because you have so much traffic, you cannot just send all the packets. But at least that is the best you can do if you don't know anything about the network, especially in wireless networks. Sometimes you have an automated flooding built in. So because of if you have an antenna, data goes anyway to all the surrounding nodes that are within transmission range. Yes, and then you overlap and cover certain nodes several times. That means you do too much. Is this a problem? Is it really a problem? Maybe you have a problem in reception. Maybe there is an issue, whatever. So maybe you're happy that at least you receive it once. So in wireless, just make a remark, if you flood, you typically repeat the packet again on the same interface you received it on via your antenna. So yes, you will always receive duplicates, etc., etc. I will come back to this flooding when you talk about ad hoc networks in mobile communication. So yes, flooding is stupid, isn't it? I mean, you flood the network, maybe for small networks, but for large networks. So obviously, flooding doesn't work at large scale. But why do I talk about flooding? Because some of the routing algorithms at least use a limited flooding. So some of the algorithms require at least some flooding, some localized flooding, so to say. And we can always use flooding as a reference for performance evaluation of routing algorithms, because we know flooding always finds the shortest path or best path, because flooding basically finds all the paths that make sense. So yeah, we do duplicate detection, all these things, but if there's a path, flooding will find it. So this is why flooding can be used to compare your whatever nice routing algorithm with. Okay, so we have to do better. Well, because of scalability, but we can compare them with flooding and see if we, with our more elaborated routing scheme, also find a path that is as short as or as good as the path the flooding found. But to talk about good or bad, we need metrics. So we have to care about specific paths and have to look at, okay, what paths are available? Maybe there's one, maybe there are several one. And if there are more than one, how do I compare them? So why is one path better than other one? So that's a good question. So routing, that takes care of question 1. So routing finds out, hopefully at least one, maybe several paths from a source to a destination. Metrics are important for the comparison. So how can I say this is better than the other? So typically what we use, well, for metric, response time, throughput, capacity, hop count, so the least number of intermediate devices, avoidance of overload, security. There's so many potential metrics that, for example, in battery-driven devices, we can have as metric use a path with the lowest energy consumption, or using only nodes that have enough capacity in the battery, etc., etc. So that's the idea. So now, what is the input for the routing? Well, it's a cost per link, and we try to minimize the cost in the end of the overall path, whatever cost here is. And the simplest approach is we assume all links have equal cost. This could be $euro, but this could be also weight, this could be load, etc. We can configure this manually, automatic, etc. So the algorithm should find paths with the smallest end-to-end cost, maybe one path, maybe several paths with the same smallest cost, or maybe the 2-3 paths with minimum cost. So end-to-end cost depend on these metrics. And what do we have? Typically additive metrics like delay. So if we try to find a path with a minimum delay, we can add the delays of the links plus maybe delays in the routers. Or multiplicative metrics like packet delivery ratio. So think of if you drop some packets, especially if you have wireless links, you drop some packets, then you multiply the costs of each link on the path. And we have metrics where you take the minimum, for example, minimum in throughput. So if you take the throughput for all the links, you look for the minimum, and then this is the overall throughput of the path. So what is the default? Default, we simply say costs are equal and we add the hop. So hop count, that's typically, if we don't do anything else, we do hop count. That's the simplest one. We can always add some other metric on top of this. Okay, sounds easy. It's not. If you know theory and computer science, you know determining the optimal path is difficult. The point is, well, one theoretical point is that some of those tags are NP complete. That means, well, we have a problem if we have a larger number of nodes. There is no efficient way of determining the optimal path. So it's really a lot of computation. But additionally, well, we don't have all the information about topology in a kind of instantaneous way. Plus the network is dynamic, plus we have conflicts between, for example, fairness and optimum. Maybe you optimize a path, but then you notice, oh, this is not fair considering the other paths. Just an example. So if we want to route traffic through this network, then, well, we could ask for what is the highest throughput between two nodes. Okay. Well, now we can additionally assume if we want to achieve the highest throughput between E and G, then the best case is no one else talks. So especially if we have an X and a Y and we try to optimize in terms of throughput this E to G, this path, then we could say, okay, no one should disturb us. wow, there's an X that wants to talk to Y. No, we do not allow this. Is this fair? Or you say, okay, then X talking to Y, please take this detour. Then I still have a big throughput. So X and Y wouldn't be happy about this, because obviously the shortest, best path for them is this direct communication, but this would influence this goal, highest throughput here. Very simple example, but you already see there might be conflicts between this optimum, achieving optimum throughput, and fairness. And this is just one simple example. Okay, so we have different topologies, fluctuating topology, it's not stable. We don't have instantaneously all the information. We have a big problem when it comes to scalability. We have conflicts, but still somehow we want to solve it. Some basic concepts you may know from more theoretical computer science. So if we look at the physical network topology, so then we can consider our routers as actually nodes in the network or vertices. And they are connected by our links, layer 2, you remember. So these are our edges. And the edges, they may have a certain weight. So in the end, what we have is then a graph G consisting of nodes, our vertices, U, V, W, X, Y, Z, and a set of edges, so the connections in between. And typically, we assign a certain weight to the edges. So weight, what does it mean? This could be the throughput, the delay, the cost, etc. And we want now to find an optimum path through this graph. That's the overall idea. Okay, so this graph now is a simple one. Now think of the worldwide internet and think of the full topology of the worldwide internet. You can imagine it's not possible to use a routing algorithm that considers this worldwide graph. So in real systems, what we do is, well, we have to at least discover a partial graph that is sufficient for the task to find a path, but we can handle it. So what you see here, the partial graph example, is sufficient to find a way. For example, if we want to go from L to M, yes, we find a way, but maybe we cannot find this short path. This could happen. So even in the internet, we do not have any instance, any node that knows the whole topology. So we have to apply algorithms that have to live with a partial topology, hopefully sufficient few, but only partial. And we still must be able to discover kind of an optimum path. Okay, we saw now many different concepts. Concepts of source routing, hop by hop, packet, virtual circuits, packet base, etc. What are the advantages, what are the disadvantages of these different concepts? So please compare. What is source routing? What is hop by hop routing? Pros, cons, packet based, virtual circuits, reactive, proactive, flat, hierarchical. Why do we go hierarchical? Why do we go proactive in the internet? Why do we have packet based? Why do we use hop by hop routing? Because we have different choices. So what can we do if we have no idea? So what does always work and what is kind of a reference here? And what are metrics, routing metrics? Why do we need them? What are examples? How can we use them?